So, we will continue our discussion on dielectric properties of solid. So, we have derived the relation Clausius Mossotti relation, that is epsilon r minus 1 by epsilon r plus 2 equal to n alpha by 3 epsilon 0, right. So, epsilon r the dielectric constant or relative permittivity, and epsilon 0 that is for dielectric constant for air or vacuum. So, it is absolute permittivity, epsilon 0 is basically absolute permittivity and epsilon r is the relative permittivity, and n is the number of atoms or molecules per unit volume, that is basically number of dipole moments per unit volume. No, that is the number of atoms or molecules. So, if each molecule or atom is having the magnetic moment mu, so then n into mu, that will be the polarization. So, P will be equal to n mu. Mu is the dipole moment, right, and alpha is the polarizability. So, that is defined, that dipole moment for unit electric field. So, basically dipole moment for a atom or ion or molecule, that is proportional to electric field, and that proportionality constant is alpha, and this alpha is called polarizability. Right. So, that is what we have discussed in earlier class. So, now this today I will discuss what is the origin of polarizability or the dipole moment or the polarization in dielectric material. So, we will try to find out the origin of polarization or dipole moment and then dipole moment or polarizability in dielectric material. Okay. So, in case of magnetic material, that we have seen the origin of magnetic dipole moment was the induced dipole moment as well as the angular momentum, dipole moment due to angular momentum. So, there this orbital angular momentum, spin angular momentum as well as nuclear angular momentum. So, that was the origin of the magnetic dipole moment. So, here in case of dielectric material, so there are three types of dipole moment or polarizability in. So, one is called electronic polarizability, electronic polarizability. Then electronic polarizability means from there basically you will get dipole moment as well as the polarization. Second is ionic polarizability, ionic polarizability. Third is dipolar or orientational or orientation polarizability. Okay. So, electronic polarizability, so basically distribution of electronic charge in atom, that is the source of electronic polarizability. So, in atom there is a nucleus and the charge is distributed surrounding of this nucleus. So, in atom center of gravity of this electronic charge distribution and center of gravity of the nucleus, they coincide. So, as a atom is neutral, as a atom it is neutral. So, when you apply electric field, then basically what happens, electric field, it applies force on positive charge and on negative charge in opposite direction. So, thus this so originally say so this is the nucleus. Now, if you apply electric field, so the center of gravity they will not coincide anymore, because negative charge and positive charge they feel force in opposite direction. So, then basically if you keep this nucleus at fixed position, then you can say that this electronic charge is displaced. Okay. So, its center of gravity of this electronic charge is say this one now. Okay. So, these are the positive plus Zd charge and this will be the negative minus Ze charge. Okay. So, then it will form dipole moment, because dipole moment you know that minus charge say q and plus charge say q plus q. So, they are separated by a distance say L. Okay. So, then dipole moment mu is basically q L. Okay. So, here there is a equal amount of charge, now they are separated. So, it will form dipole moment. So, this dipole moment mu is electronic dipole moment, it is mu, say mu. So, we will write mu e to differentiate these different kinds of dipole moment. So, electronic dipole moment. So, mu e is proportional to E, and this proportionality constant here we write alpha E. Okay. Alpha is the electronic polarizability. So, source of this polarizability is basically the electronic charge of the atom. So, it is for in case of neutral atom this dipole moment is formed, and second case is ionic dipole moment, ionic polarizability. So, that is seen for the ions basically, say for the ions, say sodium chloride, say sodium chloride HCl, okay, HCl molecule, okay. Then oxygen, then yeah, CCl4, okay. So, they are in ionic formation, and in this, sorry, yes. So, this sodium chloride, they are basically is in molecule. So, they are in ionic form, sodium ion and chlorine ion, right, HCl, H plus Cl minus, right, and oxygen also they have ionic form, means it is not in molecule, it is not neutral. Okay. So, this they shows this ionic dipole moment. So, here basically they have in ion form, they are in ion form, and when we apply electric field, then positive ion and negative ion they will be just separated, because they feel the opposite force due to electric field. So, this all ionic ion basically ionic, so all ions basically they are one is positive and another is negative. So, before applying electric field there is no dipole moment. Okay. If there is no dipole moment, then after applying electric field, so this positive and negative ion they will be displaced in opposite direction. So, this also there will be, then in that molecule, due to this displacement of ions, you will get the dipole moment. So, this is also induced dipole moment, because it is induced by the electric field. So, you will get dipole moment mu, and this if we write mu I, that is ionic dipole moment, it is again equal to alpha polarizability, ionic polarizability alpha I E, right. So, now as I mentioned that this ionic polarizability or polarization or dipole moment, we see in case of ionic ions, in molecules ions are there, both types of ions are there. So, before applying electric field, these molecules having ions, they may have dipole moment, they may not have dipole moment. So, whatever the case, whether dipole moment, original dipole moment is there or not, but after applying electric field, so we will get this induced ionic dipole moment. So, when this before applying magnetic field, if these molecules are having dipole moment, then that is basically called permanent dipole moment. and that material is called polar material, polar dielectrics, polar material, polar solids or dielectrics whatever. Okay. If they do not have permanent dipole moment, then it is called non-polar dipole moment, non-polar dipole moment, non-polar solids. Okay. Non-polar solids. Okay. So, this electronic polarization or polarizability, ionic polarizability, that is common for polar solids and non-polar solids. So, this third one, dipolar or orientation polarizability, that is for only solids which are polar, means they have permanent dipole moment. They have permanent dipole moment, like this water H2O. Water is polar material, this carbon monoxide is polar material. Okay. Yes. So, in case of water, this in case of water, this bonding, it's not bonding is not like this. Okay. There is angle, okay. So, then minus some delta amount of charge, okay. And in case of hydrogen, the delta plus delta amount of charge. So, they are separated with some distance. So, then we tell that they have permanent dipole moment. Carbon monoxide also have permanent dipole moment, but carbon dioxide do not have this permanent dipole moment, because its their bonding is, I think bonding is there is no angle. So, they do not form permanent dipole moment. Okay. So, bonding is basically put this way. Anyway, so the materials which are having permanent dipole moment, so that material is called this polar material, polar dielectrics, polar solids. Now, their dipole moment, permanent dipole moment mu, and now these dipole moments are randomly oriented in the material, or this yes. So, now if you apply electric field, then what happens? So, in this case also what happens? These dipole moments, they will feel the torque due to electric field, because torque in case of magnetic field you have seen m cross H. So, in this case it is mu cross E electric field. Okay. So, they will feel torque and they will try to align towards the electric field. They will try to orient towards the electric field. Okay. So, then you will get the net polarization or moment due to the orientation along the electric field. So, that if I tell that dipole moment is due to orientation, it is mu 0. So, that will be equal to alpha 0 E. Okay. So, this alpha 0 is called the orientation polarizability or dipolar polarizability. Okay. So, when we will apply electric field, then this materials will, the source of this dipole moment are basically these three: electronic, ionic and dipolar moment, dipole moment, and and as a whole you will get contribution from all source, you will get electronic contribution, ionic contribution, dipolar contribution, but that so total alpha polarizability of this atomic polarizability that is basically alpha E, and then ionic polarizability, that is alpha I, and then your alpha 0. Okay. So, this will be the alpha will be the net polarizability for the atoms or ions or the molecules under electric field. So, this that relation I wrote, that Clausius atmospheric relation, there this n. So, we wrote n alpha. So, epsilon r minus 1 by epsilon r plus 2 equal to n alpha by 3 epsilon 0. So, this is the alpha whatever we are discussing. So, this is the alpha. Okay. Now, you see there are 3 contribution in this alpha, but it depends on the material. In some materials there may not contribution some of them or one of them. So, so that's way. So, we generally tell that in case of elemental material or dielectrics, in case of elemental dielectrics. So, I think I can use this space. So, in case of elemental dielectrics, so there your this alpha. So, this contribution only comes from this electronic contribution. So, in that case alpha is basically only alpha I. So, there will not be contribution, so not alpha E. So, it is because there is no, it is elemental dielectrics. So, there is no ion. So, this contribution will not be there, and it is not, there is no permanent dipole moment. So, there will not be this orientational contribution. So, in that case this alpha is basically alpha E. Okay. So, in nonpolar material, in case of nonpolar material means permanent dipole moment is not there. Okay. So, another case can be nonpolar dipole dielectrics, nonpolar dielectrics, nonpolar dielectrics. So, in that case there is the permanent dipole moment. Okay. So, in that case contribution will be from alpha E and this alpha I. So, no contribution from the orientational polarization or polarizability. Okay. So, this alpha I and alpha E basically depends the structure of the atoms, ions or molecules. Okay. So, that is why it is the independent of temperature, they are independent of temperature. Okay. Independent of temperature. Okay. But this alpha 0 orientational polarization or dipolar polarization or polarizability. So, that depends on temperature, because this comes from the orientation of the dipoles along the electric field. So, if temperature is changed in these solids. So, this thermal energy, so that depending on that, so it will try to misalign or disorder this dipole moment. Okay. Just reverse of that electric field will try to align them, and thermal energy will try to misalign them or disorder them. Okay. So, this polar material, third case is polar material or polar dielectrics. In case of polar dielectrics, so this there will be contribution from all, this electronic, ionic as well as orientation, polarizability. So, all three contribution will be there. So, in that case, in case of polar material, so this alpha basically have this all three contribution. Okay. So, this now I will show that this alpha 0 is basically it's depends on temperature, and that we can show easily. Now, you see, now imagine that you have dielectrics, you have materials, this materials is having the permanent dipole moment. Okay. So, these atoms or ions or molecules are having permanent dipole moment. Okay. Now, just think about this paramagnetic material. Okay. So, there we use this term, this paramagnetic gas, means we assume that the magnetic dipole moment of each atom. So, there is the interaction among them. So, they are free to rotate their dipole moment. Okay. So, similar concept you can apply here also. So, you have now in place of magnetic dipole moment, you have electric dipole moment. In place of magnetic field, you are applying electric field. So, along the electric field, if you apply electric field in this direction, if you have dipole, so dipole will try to, there will be torque as I told that dipole, if you have dipole mu say. Okay. So, then mu cross E. So, this is the torque, it will feel that torque and try to align along the electric field direction. Okay. And so, this now same way one can find out, that is the Langevin function, you remember, in case of paramagnetic gas. So, in case of this polar dielectrics, okay, which is having this permanent dipole moment. Now, if you consider the way we derive this Langevin function for paramagnetic gas. So, just if you derive that same way, because same things, there is no difference. Okay. So, then that you will get Langevin function, and the as we found that the polarization basically, polarization in that case magnetization, in case of magnetic, in this case polarization due to orientation. So, I am writing P 0. Okay. This P 0 is basically n mu, okay, and then Langevin function. Okay. So, where L alpha is, what was that? Cot hyperbolic, it was cot alpha Langevin function, this was I think cot hyperbolic, alpha minus 1 by alpha, that was the Lagrangian function, right. So, in this case alpha was, what is the alpha? Alpha was, you remember this mu h, in this case it is E divided by 3 divided by kBt, right, kBt. Okay. Now, there will be confusion if I use this alpha here, just I have written because in case of magnetic material, paramagnetic gas, we use this alpha. So, now in this case for polarizability we are using alpha. So, let me write here just y, okay. In place of alpha, just let me write y, okay. Lagrangian function y, okay. So, let me write y, okay. And for when alpha is very less than, so not alpha, here I will write y, y is very less than 1, that means higher T at higher temperature T and lower electric field. Okay. So, we have shown this Lagrangian function, this becomes alpha by 3 means y by 3, right. Okay. So, y by 3, so y is mu a mu e by kBt. So, this solution here, this P0 we can write in mu, then mu e means mu square e, okay, divided by 3 alpha by 3 y by 3. So, 3 kBt, same expression as we get but for the paramagnetic material, paramagnetic phase. Okay. So, here this so this polarization just I do not need this one anymore. So, here this polarization P0 is basically, what is P0? P0 is n mu, right, n mu, okay, dipole moment per unit volume. So, now mu is basically alpha O E, right, polarizability. So, if you compare these two, then your alpha is, you are getting alpha O, is basically mu square by 3 kBt. Okay. So, as I told, this alpha E and alpha I, that is independent of temperature. I have not shown you, but just it depends on structure of the atoms molecules. So, that is why one can think that the structure of atom or molecules generally does not change with the temperature. So, that is why they are also independent of temperature, and but this orientation polarization, it depends on temperature. This is the expression for this. So, basically your alpha in case of polar dielectrics. So, alpha is alpha E plus alpha I, that is independent of temperature. So, so I can write just alpha dash for these two plus alpha 0 is mu square by 3 kBt. Okay. So, it depends on this type of materials, and that decides, depending on that it is decided that this which contribution will be there in dipole moment or in polarization. Okay. So, this chi is so chi, one can see this chi polarization, you know. Okay. So, chi I can I think just chi one can write this yes. So, total polarization of this polar dielectrics I can write. I think we are interested for polar dielectrics. So, total polarization, as I told, this all types of polarizability will be there. So, this polarization N, then N alpha E, right. So, then N alpha E basically N alpha alpha E plus alpha I plus alpha 0 and that is I can write N and E, I have to write E, sorry. Yes, E will be there. So, this basically N then alpha dash I will write, this independent of temperature one part and this temperature dependent part is this mu square by 3 kBT, okay, 3 kBT. Now, this chi is defined, chi susceptibility is defined is basically P by epsilon 0 E, P by epsilon 0 E, right, and that is equal to P is this and E is there, okay. So, then I will get basically N by epsilon 0, E will go and I will get alpha dash plus mu square by 3 kBT, okay, 3 kBT. So, if I plot chi versus 1 by T, chi versus 1 by T, okay. So, what I will get? So, in case of non-polar material, so this contribution is, so it will be independent of temperature, so I should get this type of curve, right, because this part will not be there. So, anyway, if you do experiment on a dielectric material and if you get the curve like this, so then you can conclude that this material is non-polar material. If you get the curve like this, okay, then you will tell that this is a polar material, and it varies. So, because 1 by T, right, 1 by T you are here. So, you will get this will be the slope, this into this N epsilon 0, slope will be N mu square by 3 epsilon 0 kb, okay, slope of this, and this intersection here, this N alpha dash by epsilon 0, okay. So, then you can tell this is the polar dielectrics, and from the slope one can find out, in principle one can find out this dipole moment, okay, and this from intersection one can find out this polarizability, which is independent of temperature, okay. So, I think that is the things one can find out from the study of the dielectric material, and from experiment one can tell whether it is polar material or whether it is dipolar material. So, I think I will stop here, then I will continue in next class. Thank you.